On the 26th of April 1986, a nuclear disaster at the Chernobyl nuclear power plant occurred. The operators of the plant started a simulation of a power outage to expand their knowledge about the safety measures that should be done in controlling the plant without power. After disabling the reactor safety systems, the power level of the reactor unintendedly dropped. They tried to restore the power, but it only resulted into a highly unstable reactor. A series of unfortunate events happened, ending with the reactor's core to explode. This accident caused the death of approximately 4,000 people and the creation of a 2,600 km square exclusion zone. This exclusion zone prohibits the public in entering the highly contaminated areas around Chernobyl. Before allowing the exclusion zone to be habitable by the people, the radiation level of the zone must be weighed out.
A number of dangerous radioactive elements are found to be spread all throughout the exclusion zone. Some of the most notable elements are iodine-131, cesium-137, strontium-90, and plutonium-241. Of all the mentioned elements, cesium-137 was recorded to have the longest half-life of 30 years. According to an article published in 1989 from the Joint Publication Research Service, the approximate radiation level in the vicinity of the reactor core is 300 sieverts per hour, or 2.628 times 10 raised to 9 millisieverts per year. Sieverts is an SI unit used in measuring a dose of ionizing radiation. In present times, the global average exposure of humans to ionizing radiation is about 2.4 to 3 millisieverts per year. About 20% of it comes from exposure to man-made radiation sources, while 80% is accounted from nature. With all the information laid out, our group's objective is to find the possible time for Chernobyl to be inhabitable. That is, to solve for the time it takes for cesium-137 to reach radiation levels of 3 millisieverts per year. The group has 4 key assumptions in solving this problem. Number 1, the radiating material that should be accounted for is cesium-137 since it has the longest half-life. Number 2, the measured radiation level at the vicinity of the core is only from cesium-137. Number 3, the decrease in levels of cesium-137 is only because of half-life and not other factors. And lastly, cesium-137 decays at a constant rate.
We will now find out how to solve the time it takes for cesium-137 to reach radiation levels of 3 millisieverts. As with any other math problems, we must first find out what are the givens. We let x to be the radiation level, then, at initial conditions, we let x to be 2.628 times 10 raised to 9 at t equals 0. Knowing the half-life of cesium-137, it is implied that after 30 years, the radiation level is now half. Knowing all of this, we can now solve for t at x equals 3. Now that we know all of the givens, we can now identify what formula to use for this problem. For this problem, we can use the differential equation of the exponential decay formula, which can be represented by dxdc is equal to kx, k being the rate of decay of the variable x. Now, what we have to do is convert this into a variable separable by dividing it by x and multiplying it by dt. After that, we have to integrate both sides. Integrating both sides would give us ln of x is equal to kt plus c. After that, we multiply e to both sides, giving us x is equal to c1 e raised to kt. Remember that we can play around with the constant. After that, we can now plug in the initial conditions of x is equal to 2.628 times 10 raised to 9 at t equals 0. Doing this, we can now find c1. Plugging in the initial values would give us 2.628 times 10 raised to 9 equals c1 e raised to 0. c1 now is 2.628 times 10 raised to 9. We input it back to the original formula, giving us 2.628 times 10 raised to 9 e raised to kt equals x. Now we only have 2 unknowns. But remember that we have another condition, which is x over 2 at t equals 30. Doing this, we can now find k, which would give us a value k of negative 0.0231. Now that we know k, we can now solve for the problem, which is finding t when x is equal to 3. Plugging in all of the values, we now have only one unknown, which is t. Then, solving for t would give us 891 years. Meaning, after 891 years of when the Chernobyl reactor exploded, that is when Chernobyl can be habitable. Meaning, at 1986, we add the 891 to it, it would be equal to 2,877. Meaning, at this year, Chernobyl is now habitable. and that is how you solve the problem.